Welcome to our explainer on modern automated transit. Have you ever stood on a metro platform, watched one of those driverless trains glide perfectly into the station, and just wondered, how on earth does it actually know exactly where to stop? Or, for that matter, how it avoids the train that's just a few hundred meters ahead of it? Today, we're going to unpack the invisible, highly complex network that makes high-frequency, autonomous train travel possible. We're looking at a system that allows trains to operate safely and efficiently without any human drivers, running closer together than ever before.
Okay, let's dive right into this whole ecosystem. Think of this as the master blueprint of a modern transit network. Notice how it's basically divided into three distinct layers. We've got the train at the bottom, the trackside equipment just above that, and the control center presiding over the whole shebang. It's a system where the train, the track, and the control center are constantly talking to each other. They're exchanging vital data multiple times a second, just to ensure millions of commuters get to work safely.
The name of this technological marvel is Communications-Based Train Control, or CBTC for short. Now, to really appreciate this, we kind of need to understand what it replaced. Older railways used fixed-block systems, basically allowing only one train per static section of track. It was safe for sure, but incredibly inefficient. CBTC actually abandons that entirely for moving blocks. By using continuous, high-bandwidth radio communication, the system creates this protective, virtual bubble right around the moving train. So, as the train speeds up or slows down, that protective block moves and resizes right along with it. This maximizes track space and radically increases the capacity of the entire line. So, here's what we'll be covering. Number 1, onboard, train equipment. Number 2, Wayside, trackside systems. And number 3, OCC, the central brain. Section 1, onboard, train equipment. Inside the sleek shell of a modern transit vehicle, well, there's some serious hardware. The major onboard components act a lot like human senses and local reflexes. We have the Vehicle Onboard Controller, or VOBC, which is basically the brain of the train itself. We've also got tachometers to sense motion, Balise readers to spot landmarks, antennas to communicate, and the train operator display for human staff to interact with. The undisputed star of the onboard equipment is absolutely the VOBC. This is the vital onboard computer responsible for precisely determining the train's location and implementing automatic train protection and operation. And what's really fascinating here is that safety in railway engineering relies heavily on redundancy. So each train doesn't just have one VOBC, it actually carries two of these controllers in a hot standby configuration. If one experiences even a tiny glitch, the other one instantly takes over, guaranteeing incredibly high availability and an unbreakable safety net. Think about where all this hardware actually lives. The VOBC units are tucked securely into the train car, directly wired into the automatic train protection and operation modules. And those antennas mounted on the train? Those are the crucial data communication lifelines. They facilitate the constant, rapid-fire radio communication with the Wayside, making sure the train is never, ever flying blind. But how does the train actually know where it is? Well, it relies on two contrasting sets of senses. First, it uses tachometers and accelerometers. These are basically wheel sensors that measure how fast the wheels are turning to gauge speed and the relative distance traveled. But wheels can slip on wet tracks, and that throws off the math. So we contrast that with Balise readers. These are scanners under the train that read physical tags, called Balise or transponders, that are bolted directly to the track. When the train passes over a tag, it gets an absolute, undeniable location reference to correct any drift in its onboard math.
Now you might be wondering, but this is all fully automated. Why do we even need screens in the cabin? Well, even in highly automated driverless systems, the train operator display, or TOD, serves as a really vital interface. Should a human attendant need to take over or simply supervise the system, the TOD provides a clean, immediate read on the maximum permitted speed, actual speed, target distance, and vital door status. It's essentially the ultimate dashboard for human oversight on the move.
Section 2, Wayside, trackside systems.
The Wayside is really where the track itself comes alive. It's not just steel rails and gravel anymore, guys. Scattered along the tracks, we have critical infrastructure that manages safety for specific geographic zones. The major players here are the zone controller, the interlocking systems, a network of radio access points, and various other vital trackside equipment.
The absolute authority out on the track is the Wayside Zone Controller. Think of it kind of like a regional air traffic controller, but for trains. The zone controller constantly receives location and speed data from all the trains within its specific geographic area.
It processes this massive amount of data and issues something called a movement authority limit back to each train. This limit tells the train exactly how far it is safely allowed to travel, ensuring trains never, ever get too close to one another.
But what happens if the cutting-edge radio system experiences an issue? That is exactly where the computer-based interlocking steps in. Interlocking serves as a vital, physical fallback system. It's the essential trackside equipment that physically aligns the tracks by controlling the point machines, the mechanisms that actually switch trains from one track to another, and operating traditional signals. It acts as an unyielding physical safety net right beneath those invisible radio waves.
Now, what's really interesting here is how the system maintains that perfect radio connection. These Wayside radio access points are basically rugged, highly specialized Wi-Fi routers placed all along the tunnel walls or tracks. They create alternating, overlapping cells of radio coverage. As a train speeds down the track at, say, 100 kilometers an hour, it seamlessly hands off its connection from one access point to the exact next one, with literally zero data loss. If one radio unit fails, the overlapping coverage from the neighboring unit ensures the train never drops its connection. Pretty cool, right?
Section 3. OCC, the central brain.
This is the highest tier of the architecture. This is where human intuition meets massive computing power. The major components in this nerve center include the ATS servers, rows of highly specialized operator workstations, and comprehensive network management systems. At the core of the OCC are the Automatic Train Supervision, or ATS servers. The ATS servers are literally the master schedulers of the entire system. While the zone controllers ensure trains don't crash, the ATS ensures the trains actually run on time. It executes the daily schedules, automates complex routing, and brilliantly, it adjusts operations instantly during anomalies. So if a train is delayed at a station because someone held the door, the ATS instantly recalculates the speeds and dwell times of all the other trains on the network to prevent a massive cascading traffic jam. Inside these operational control centers, it's an incredible workstation environment. Massive panoramic display screens give human operators a literal God's eye view of the entire transit network. Through the ATS data and live CCTV feeds, operators can monitor the real-time health of every single train, every track switch, and every station platform simultaneously. It's a high-stakes, information-rich environment completely designed for total situational awareness.
Operating quietly behind the scenes of those giant screens are the network management systems. Now, while they aren't driving the trains directly, these systems and data gateways are absolutely vital. They monitor the continuous health of the routers, switches, and fiber optic cables. They provide robust cybersecurity firewalls and ensure the massive, relentless flow of data remains secure, uncorrupted, and uninterrupted. Without this digital backbone, the entire system would just go blind.
So the crucial point here is how these three distinct tiers unite. The onboard tier provides the action and the senses. It measures speed and physically applies the brakes. The Wayside provides local control and safety, acting as the immediate referee, determining who can move where. And the OCC provides global supervision and scheduling, keeping the entire ballet running smoothly to the timetable.
Let's see how this all builds in real time. Imagine just a single piece of location data. Step 1. The train reads a tag and its antenna blasts that data out. Step 2. A Wayside access point catches that radio wave and converts it into data on a fiber optic cable. Step 3. The zone controller receives it, verifies it against other trains, and updates the local safety map. And finally, Step 4. The ATS server receives that map, calculates a response, and sends it all the way back down the chain. This entire journey happens in a fraction of a second, continuously, all day long.
It truly is a marvel of decentralized intelligence. But, it leaves us with a really important thought. As our transit networks grow ever more autonomous, interconnected, and reliant on these continuous data streams, what fail-safes are truly necessary when the central brain goes offline? How resilient must our physical interlocking and onboard safety nets be to protect us when the invisible network falters? It's a fascinating engineering challenge for the cities of tomorrow. Thank you so much for joining me on this explainer, and definitely keep your eyes peeled the next time you step onto a platform.